Hey guys! Welcome to virtual day homework because like virtual day already happened, but we're gonna do a little extra. So the homework part. I've logged into the Pearson thing right here. This is the virtual day homework 17 right there. And this is the first one, 4.15 of the Pearson stuff. All right, so here we go. This is the first one. Actually has some math and it's a little bit confusing-ish because it refers back to last chapter with kinematic stuff. And I keep looking down because I got my stuff printed out right here so I can look at it and I worked it out ahead of time. So I'm ready. Here we go. The first thing is you got this. It says calculate the acceleration of a 1,400 kilogram car that stops. So we know the final velocity, they tell you right there, is going to go till it stops. So the final is going to be 0. It's going to go till it stops from, for mine right here, it says 39. Up here it says 31 kilometers an hour. So I'll use the new number, 31 kilometers an hour, and it stops on a dime. And then they tell you that on a dime is 1.7 centimeters in thickness or length or diameter or whatever. So we got to use those things. So they tell us, let me click on here, get a little highlighter dude moving around. All right, so they told us the speed right there, but the important thing about that is they didn't tell us in the correct units. We can't handle centimeters and kilometers together. So we're just going to make both of them match and go to our base unit that we're happy with, which is meters. All right, so using that whole dimensional analysis thing that you guys love. I know you guys remember that goodness right there from your chemistry and previous science and everything. So I'm going to start off with my 31. Make sure you're using your numbers because even with mine, I printed it and it was 39, but right here it says 31. So use whatever your number is on your numbers. That's important for getting stuff right. Okay. All right. So I'm going to change my color, which is going to be blue is good. All right. So 31 km over HR. They say just H, but I like to say hours because sometimes later on we're going to have stuff that has height in it, and that's just going to be H. So when you say HR, all right, we want to cancel out the kilometers. Next time you see the kilometers on our little chart right here is going to be on the bottom. km. That's going to be 1 kilometer for how many meters? 1,000. Good job, right? So 1,000 meters. Cross out your kilometers. Now we're going to cancel out our hours. Next time you see hours, it's going to be on the top. So that's going to be 1 per and 3,600 seconds. Kilometers per hour all the way down to meters per second. So then the hours and the hours going to cancel out. And then the shortcut for doing all of this, now that I've showed you the dimensional analysis part, is that 1,000 divided by 3,600 turns into all of this right here, divided by 3.6, right? Because it was 1,000 divided by 3,600, so it turns into divide by this equals your meters per second equals. All right, so this number, divide that. Got my handy dandy calculator ready. So here we go, on, clear, 31 divide 3.6, and mine is 8.61 meters per second. All right, this is not the answer. Don't go ahead and type that in there right there. That is just the start velocity. They told you that speed in kilometers per hour. We had to change it to meters per second. So this right here equals VI. And I'm going to erase all this because you can just rewind to it if you need it. All right, so that's the start velocity. They told us the finish velocity is stops 0, right? So we have start and finish, and we have a distance. Mine is 1.7 right there, and it was 1.7 right there, so it's probably the same for everybody because a dime isn't going to change size for everybody. They try to use real numbers mixed in with the made up numbers every now and then. So we have those things, and we want to know, we want the acceleration. We have distance, start velocity, finish velocity, want the acceleration, and that turns into this over here equation. I don't know if you can see that really well up there. Yeah, it's there. All right. So I'll scoot that over a little bit, and I'll do some math on the board with that. So this is the third kinematic. We have our final velocity going all the way till you stop. So 0 equals the start velocity for me that I calculated right there was 8.61 squared plus 2a. We want the a. We don't know the a. And then the distance is 1.7 centimeters, but we're going to change that to meters because they don't match up, right? This is meters per second, and we want the centimeters to match that. So this is going to be 0.017 meters. I did that little fancy divide by 100 fast right there, right? So Matthewness is going to do some fancy rearrangement. So you're going to have negative 8.61 squared equals 2.017 and a. Now I'm going to divide all of this over here. 2.017 with your parentheses. This cancels out. So if you have the fancy handy-dandy calculators that can program all of this in at the same time and hit enter, it's going to be this squared divided by double of the distance equals the acceleration. And that's what we're trying to find. So I'm going to type it in. So give me a second while we're doing some boring TV for a second while I type in some numbers. 8.61 squared divided by 2 and 0.017, and I get 2,180. So A equals negative 2,180 meters per second per second. Do you have to put the units on there? You do have to put the units on there. I don't think that they're going to like the meters per second, but I don't know. So close, click, click. See that I did my math the right way. I got, they want how many two significant digits? So mine's going to be 2200. And then I got to get to my units. It's going to be meters. And then I don't have my mouse. Got it. Got my mouse. All right. And it's going to be per second with the little handy dandy dude right here to the power of 2 and go. Oh no, I did something wrong. Oh yeah, it's negative. I wrote negative over here. There's a negative right there. I should type my negative, so that's important there. Since it's slowing down, you're getting slower. You got to have your negative in there, and yeah, submit. Green, correct. Meter per second squared. All right, so make sure you round the right way and everything to be all right. B says, how many G's is that? So if we're going to compare this to how much gravity you would be feeling if you were experiencing this, is kind of a lot. All right. So regular gravity, according to the textbook, and in real life is 9.8. So if you take your acceleration that you calculate, I want to use the number that I had. So for me, get my pen thing going again. There we go. This guy. And scroll this up. And scroll first. B. All right. Okay. Color green, no, blue again. All right, so I had negative 2,180 meters per second squared. That's the acceleration that we had for A, or at least I had for A, equals A acceleration. All right, now we want to know how many G's that is. So this, if 1 G is 9.8, we're going to compare that to this. So all of this divided by 9.8 is going to equal how many G's? G's. With my awesome handwriting. All righty, calculator right there. Divide 9.8. I got 222. 222 G's. I hope that's an easy one for you, and just follow the little thingy there. But then there's part C. All right. Now I want to know, what is the force that the person that's in the car is going to feel? So the person, if they're in the car that's going that fast, they're going to be going the same speed as the car. So if they're going to slow down the same as the car, they're also going to have the same acceleration as the car. So we have this acceleration right here on the person. And now we're going down to the easy math of the unit, which is our second Skendel's law, F equals ma, F ma, right? So we get rid of that, and we have F equals ma. We have the acceleration in part A, so we have that. And then the my guy right here is 63, but Earlier it was 66 for me, so it does change. The mass is going to change. Make sure you're using your mass of your dude that they tell you, right? Your race car driver, person. Could be lady, could be lady. All right. So F equals for me is going to be 63, 63. And then my acceleration is everything I had up there. So negative 2180. And so all that multiplied together is going to be your giant force. It's going to be a nice, good sized number. On here it says 10 to the 5, so it's got some good numbers on there. So 2180 times 63 and 13734. So 1, 2, 3, 4, 5 times 10, 5 newtons. All right, now I'm going to work on typing that stuff in to make sure I get my green arrows. Where's my mouse? Is my mouse gone? There's no mouse. All right, I didn't write that down, so I gotta. All right, so 1.37 times 10, 5, and then where is my mouse? Mouse. Okay, click. 2, 2, 2. Submit. Yep. Okay. Whatever. And then this one, the force. If they're being all specific on their numbers, they say negative. Yep, they say negative because it's going negative. You have a negative force slowing you down. It's going to be pushing you backwards. So negative 1 point. Actually, you don't have to do the times 10 stuff. You can just do all the numbers that you have. So let me get the little decimal out there. 13700. 1, 2, 3, 4, 5. That should be good. And newtons. If you don't capitalize your N, it doesn't like it, so you got to get capital in there. And submit. Likes it. All right, so they wanted me to round up a little bit, but whatevs. I just follow directions, okay. And next, that was the first one. And that was the starting off with a rough one, but otherwise after that it gets easier. So we got some good stuff right here. This one has some weird wording to it. Yep, the tension of the rope thing. All right, so since it's a massless rope, perfect metaphysical type thing, that's saying that this thing has no mass, it's hanging down. Actually, I'll just, I don't have a thing. Yeah, I do. Thing. No, I don't. It's gone. All right, I didn't prepare a string. Whatever. I got a thing. Here's the thing. I got this thing and it's hanging down. And if this has no mass, then it's not contributing to the forces that are happening. This has no weight, no mass, no weight. In real life, this right here is holding up only the piece of lead down below it, so it has a very small force on it. But up here, it has to hold up all of that, so it kind of has more force up here than it does down here. But we don't have to worry about that in this. This is a special case in the little rope right here. A massless rope has no force addition or taking away stuff, just only going to be holding up the stuff that's going on. Okay, so they have all these words in here that go along with the story. If you read all of this stuff, it says at point A, blah, 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 all these things. I'm going to give you the shortcut version of what they're saying right there in all those words, because those words are weird. Okay, so first question says, what is the magnitude of FAD? How much is that? The magnitude is just how much, no plus minuses or anything like that. All right. And then the handy dandy thing of that is whatever force is happening right here at the 1 is going to be the forces happening everywhere. So they told us in the little story up here that it is T1. So you got to get your I don't know if it's a regular T. It might not take that, but we're going to try because it might have to do with like a tau or something. And T1, submit. Likes it. Okay, yeah, just a regular T. What they told us in the story up here that this point right here, point 1, is experiencing a tension of T, or a force of T1, tension 1. All right, and that's going to be the force that's happening along the whole thing. And so now they talk about later on. It says what's the magnitude in the words that's happening on section B, and then in terms of tension 1, right, and how much compared to tension 1, it's going to be the same. So it's going to also be a T1. So T and subscript 1, T1, submit, nice and easy. Hopefully, I mean, the understanding hopefully makes sense. If someone's pulling a rope and they're pulling 100, and then there's going to be 100 newtons of force traveling along the whole piece of rope to the other person, and they are also going to feel 100 newtons of force coming from you. You're pulling 100 right here, and ropes and things are magic because they're able to transfer that force that I'm pulling right here all the way to the other thing that's being affected. So it's affecting the whole rope thing. Right now they're talking vertical, but same thing, right? The magnitude of the upward force of this, or on point C, and this one right here are equal because of which laws, right? So the first law is inertia, right? Things want to keep on doing what they're already doing. Second law is the scandalous 1 F equals ma, and then the third law is action reaction, and it says because of which one they're equal, it's going to be action and reaction, right? If you cause a force, the other thing obviously is going to be the same. So third. Hiya. So I hope that makes sense. Action, reaction, things are equal, opposite, action, reaction. My hand pushes this hand pushes this hand, equal, opposite amount. I push the TV, it's pushing me back the same amount. Okay, rope thing, same. And Mario in the background today. All right. The magnitude of the force of BU is equal. Right, they're all going to be the same amount of force. It's like some weird words, but if there's no mass happening on the rope, then whatever force is happening here is going to be the same force happening here, same force, same along the whole thing. Clarifying that one a little bit. Now consider these. They're going to be equal. We just said that a second ago. And then check all that apply. This is where we start losing some people's. Turn my page. All right, push part F, right? Part F. All right, so. The ends of a massless rope are attached to 2 stationary objects. So both pieces of this rope right there and then the rope right here, both of those pieces are attached to chunks of mass, thing 1, thing 2. All right. Now we're talking about so that they are making a straight line. To pull all nice and set, the situation which is true. All right. So check all that are true. The tension in the rope is everywhere the same. We just talked about the second one. Everything, right? Same. The magnitude, the amount, the quantity of the forces exerted on the 2 objects by the ropes are the same. That's the same as that, right? The amount of force is the amount of tension. So, the forces exerted on two objects by the rope must be the opposite direction, right? So if you have thing 1, thing 2, this one is feeling the rope pull that way, and this one is feeling the rope pull this way, right? They're feeling, if this one is pulling this way, the rope is pulling it that way, and if this one's pulling this way, then the rope is pulling it this way. So they're happening the opposite ways, and I hope that makes sense. I'm not holding a thing, but okay, so that one is also yes. And we got the last one. The forces exerted on the 2 objects by the rope must be in the direction of the rope. And I think that makes sense too, right? If the rope was pulling that way, then the force this feels is going to be going that way. It's going to happen the same way. So, it's all of them. This is a jerky question, make you choose all of those things, make sure you got them all right. But, it's there, okay. Sometimes textbook questions are nice and precise and everything like that. So now we're on to free body diagrams. Free body diagrams, all right? You have to be able to draw these and label these in the future. And I'm super guaranteeing that there will be one of these on the AP test of some kind of thing. You have to label the forces or figure out what forces are happening on it and understand what's going on with your forces. Learning goals, things. All right, so here's they had all those words up there, and then you have, it's right here. All right, got it. So this guy named Chadwick, there he is. He's got Chadwick right here. It's almost my name. My name's not Chadwick, so don't call me that. All right. So Chadwick's pushing the piano across the level floor, and the piano can slide across the floor without friction, so that's magic, right? In real life, there's always friction, but in this case, they said there isn't any friction on the piano. So he's got special friction shoes that make him grip, but the piano doesn't have any of that. So just look at the piano. All right, and so he's applying the force to the piano. What's the piano's acceleration? And that's just F equals ma, right? And then, so here we go. So determine the objects of interest. What thing are we looking at? If we're talking about the story right here, we're talking about the piano. So we're going to choose the piano. I hope that makes sense. He's pushing the piano. Want to know how much you want to know what's the piano's acceleration? That's the thing that you care about. You're looking at what's the piano doing. So the piano. What are the forces happening on the object of interest? So it tells you not the answer right here, and yeah, it's the piano. We did that part already. So what's happening to the piano? We only look at what's happening to this. And so anything that's happening, anything besides the piano, we don't want that. So acceleration of the piano, turns out that's not a force, so don't choose that. Acceleration, not a force. It's happening to the piano, but not a force. Gravitational force acting on the piano's weight. That's a force that's happening to that, but there's no picture of it right here. But hopefully the weight / gravitational force is happening. Speed of the piano, not a force. A gravitational force acting on Chadwick. This guy's is his weight affecting the piano? Okay. The force of the floor on the piano, the normal force, is the floor pushing on the piano. So that one we care about. The force of the piano on the floor, that would be the force that's pushing on the floor. So it's a weird wording, but we don't want that. So that's what's happening on the floor. So we don't care about that one. We only care about the stuff that's happening to the piano. Even though the piano is doing it, it's not the force that we care about. We only care about what's happening to the piano. All right. The force of Chadwick on the piano is he touching the piano and pushing it? We care about that one. And then the force of the piano pushing on Chadwick. So the piano force is pushing Chadwick, so we don't care about that either. So those are the ones we care about. And green. Okay. If I'm going too fast, just rewind me, and you can remind me in email that I said awesome things that, okay. All right. All right, so now it says select the best diagram for the free body scenario, and this is the kind of thing that you have to be able to do, right? So now the dot is the piano. Look at that beautiful piano right there. I see that dot, it's piano, that's a piano, right? So we pretend that all the mass of this thing is happening at one spot. Bam, there it is. Now we care, whoop, I clicked it, but whatever, I can change it. So we know that there's weight and normal force. There is going to be those two. Those two are going to be there. But then is there anything else? This one has a pushing force. This one has the size of the arrow is important too. Just looking at this right here. So now, if the weight is small and the normal force is like this, then according to this picture right here, it is being lifted up, but that's not what's going to happen. So it's not that one. And then right here, the weight is more than normal. So this is saying that it's going down. And the other one that's nice is this one where those two are canceling each other out and you're going horizontal. So that one, yup, I clicked it. Yep, okay. Determine the objects of interest in the situation. And for this free body diagram, it's going to be the piano because we haven't talked about anything else yet. Oh, wait. All right, so now we're on the new picture. Here's the new picture. I didn't change the picture yet. So I don't even think it says figure 2 right there, figure two. So there's the new picture. Now it's going up a ramp, and we're talking about what's happening to the new thing. And then now it says, is Chadwick strong enough to push the piano up the ramp alone, or must he get help? And it also has no friction and blah. So there's our picture and everything. All right, so we're still talking about the piano. So it's piano. Yep, okay, still talking piano. And it says, which diagram of this one? So remember on ramps are a little bit weird, where you have to make your x, y match the surface of the ramp. So our ramp is this way, right? So now this is the y and this is the x. That's to match the surface of the ramp. So this right here doesn't match the surface. These kind of do, and no, this one kind of does. So it's either between this one or this one, which is B or D. It's B or D, right? So is he pushing exactly horizontal this way, or is he trying to make it go up the ramp? So I think it's that one. It's going to make it go up the ramp. So normal has to be perpendicular. That's like the definition. Normal is orthogonal. Vocab word I learned from Miss Muller. Miss Muller taught me that. Orthogonal means perpendicular. Normal means perpendicular. Perpendicular to what? The surface. So you got your ramp perpendicular to that, matches your normal. So that's good. And then he's pushing that way, which is way this way is going right here. So And now we're zooming along. I don't know if I'm going fast. If I'm going too slow, just change the little thing at the bottom to play faster, and you can watch me move around like crazy pants. And I think it's fun to watch it too that way. All right, so there's this box, and it weighs, mine is 82, but before, this is another one where the number changes on, I got all these pages, right? So my previous one was 72, but this one says 82. So the weight of the box is going to change according to what you got. So just make sure you're using your numbers. All right? So it's at rest on the table. Keywords at rest means not accelerating. And yeah, at rest. In this scenario that we're talking about is not accelerating. The rope is tied to a box, runs vertically over a pulley, and this has a weight hanging right there. So this thing right here is being pulled down by gravity, and because that's being pulled down, it is pulling up on this. That's how pulleys are. Pulleys are magic. They change the direction of forces. So this one right here has a downward force. This one has a downward force that is causing an upward force on the box. So I'm gonna draw that in my little. Where's my little thing to draw? Is it gone? Do you see it? It's gone. I don't see it. Well, whatever. I'll just point. All right. So this down force going over the pulley around this way is an upward force. Like, does that make sense? The rope is coming around this way and it's being pulled down this way, down. So when you bring that backwards this way, it's being pulled up. These pulleys are magic. Okay. So it says that the weight hanging right here is 30 newtons. It's 30. So this one, the box has an upward force of 30. And with all of that, you're going to add up to 0 in the y direction. So I'm going to draw my picture of the forces and our cool equation. We don't need this equation anymore. All righty. So we have a net force of 0. That's our cool, important equation we're looking at. So F net in the y direction equals 0. And if you look at this guy, he has, can I scroll a little bit? Scroll. No, but it's right at the edge of the table right there, right? So when it is like that, back to A, okay. All right, we have weight, we have the surface, normal force, and we have the rope, so there's 3 forces. So we have equals F1 plus F2 plus F3, and my marker's dying, so I'm getting rid of this guy. And I'm going to use this guy. F1, I'm going to do all the positive ones first so I can have my nice order of operations of the weight being last and minus. So I have Fn, the normal force, plus the tension, plus the force of the weight, but that's down, right? So it's going to be a minus. And then so now I'm going to put in my numbers that I do know, equals 0. 0 equals Fn. That's what we don't know. We want to know, this first one says, what's the force that the table is doing? The table is pushing is the normal force, the support force, plus 30, or at least that's what mine is, minus 30 right there. And then over here, it's also 30. So that's probably going to stay the same for everybody. It's nice. And then you have minus your weight. Mine is 82 over here. 82. So these two combined are basically going to equal what that one is. And normal force is going positive. So whatever we get right there. This 82 subtract 30 is going to be 52. That's going to be the answer. And it's going to be positive. At least that's for me. My numbers. You use your numbers. Alrighty. Click. And 52. And click. And newtons. Yaha. All right. Now we switch out the hanging weight. Instead of a 30, now it's a 60. So this right here is the new number. It's going to be a 60. And that's just going to take 30 off of this. Now it's 22. I hope this makes sense. We're just doing the same equation, except for we're taking that weight off, and now you put a bigger one on there so that this feels lighter according to the surface it's on. On the table, it feels lighter. So this one is 22 newtons. All right, here's where we get fancy. This is where we get fancy, right? Now the hanging weight is 90. 90 is more than my weight right here. So if the hanging weight is more, it will go up, right? If this is more, that will go up. It's like a little fancy pulley balance system where this is going to be able to pick that up. If this is picked up, is it touching the surface? So if it's not on the surface, there is no normal force. So there's no normal force on this one. They're trying to do some fanciness over here where people are going to do the mathiness like that. And they're going to get a negative. The floor can't push negative. So, I mean, it's not pushing down. The floor isn't going to, unless it was glued to the ground and be like, how much is the floor pulling it down? That'd be special. But it didn't say it's glued down, just a box. So this one, if it's picked up off the ground, it's going to be 0 newtons and newtons. Yay. All right, moving along. That one was a fancy one at the end, and we haven't talked about tension before, but there we go. All right. A downward force of magnitude 5 is exerted on a book by the force of, right? So if you just have this picture right here, there's a book, and there's a downward force by something. What's causing it's going to be gravity right here. And then according to, it's the force of gravity, but also there's we don't call it the force of gravity. Gravity is not a force. So we're not going to, okay, gravity is acceleration, meter per second squared, but the force of gravity is weight. So if it said weight, that's what I would choose, but whatever. Okay. Little explanation in the middle there. An upward force of magnitude is going to be the same thing. It's going to be 5. If that was 5, it's going to be 5. So it's not the 6, it's not the 6, and it has to be that right there, one of those two. And it says exerted on the, right, an upward force of magnitude 5 is exerted on the blank by the table. So it's not going to be the table pushing the table, it has to be pushing the book. So 5 newtons pushing on the book. It's going to be that whole action reaction thing, right? The book is pushing the table, table's pushing the book. Okay. Do the downward force on part A, the weight, and the upward force on part B constitute the third law, action and reaction. Kind of, but they want you to say no because they're specific. But we also haven't talked about gravity yet, so we're going to have a little mini thing of that right now, right? So mass attracts other mass. This is Newton's universal law of gravitation, and we're going to do a little bit right now because we're not talking about that stuff. So this is why this one's a weird one, because we haven't talked about gravity yet. But when you have one mass and you have another mass, they are going to be attracted to each other because of gravity. So just like right now, wherever you are, there is some distance between us and everything, but you have mass, I have mass, and we are literally attracted to each other. I am being pulled towards you wherever you are, and I'm getting closer and closer. Not really, because there's enough friction to cancel all that out. So gravitational force is really weak compared to all of our other forces right now. But what we feel mostly is the Earth. The Earth is pulling you like a maniac because it turns out it's kind of huge compared to you. So the gravity that the Earth makes compared to, well, not fully, the gravity that the Earth makes is more than the gravity that you can make, but the force that you feel on each other is equal to what you feel. So we're going to talk about that explanation of why that is later on, but there's my little bit of explanation there. So the book is attracted to the table because of gravity, but that's not the force that we're talking about. We're talking about the book being pulled down because of gravity of the Earth, and so that's why it's not an equal opposite action reaction. The action reaction of the book being pulled down by the Earth is the Earth being pulled up by the book. And so that's kind of a weird thing. We're going to talk about that later on, but that is a fancy little technicality right there. So we'll explain that more. The reaction of the force in part A is the force of, it's going to be 5 again. Yeah. Okay, so that's what we're talking about, right? So the book is being pulled down by the Earth, and so the opposite of that is going to be the book is pulling the Earth up. So it's going to be, I didn't read everything, so I'm picking one. Let me see. I'm not going to waste my thing there. It's this, and it's this. Aha, okay. So the reaction to the force in part A is the force of the magnitude of 5 newtons exerted on the Earth and by the book, and it's going up, right? So that's what I said. I feel like the wording of that is kind of crazy. So the book is being pulled down by the Earth is being pulled up by the book. That's what they're saying in all the words right there. The reaction to part B, all right, so now we have the book is pushing the table is pushing the book. I don't have my stuff from right there. That's right here. It's going to be the table pushes the book, and it's that one right there. Yeah, all right. So direction force of part B is the thing being pulled down. It's going to be the table pushing it down. No. That's just, you can count my answer, whatever. Their action reactions are opposites. This is just weird wording. We'll ask you a better one when we ask you for real. Which of these laws can be used to predict the forces of part A and B? So like if we're actually going to find out how much force there is, there's the whole inertia thing. Things want to keep on doing what they're already doing. And then with that, if you apply a force to something, it's going to change what it's doing. The scandalous FMA, scandalous one. All right. So which of these laws can be used to prove that they're equal and opposite? All right. So if you don't accelerate, you're going to have your whole inertia thing going on. So that's that. It's at rest, and it's staying at rest until a force comes along and changes that. And then we could figure out the mass times gravity, and then the whole how much does it weigh, and then the normal force. We can calculate that too. So that's the second law. And then the third law, this little scenario right here doesn't really talk about that one, of how you can prove the laws that they're equal and opposite, but it's those two. So then the last one, which one says that they are equal and opposite? That's like the statement of it. That's the third. That's just a weird question. These two are a little bit worded funny, but you'd be all right. I got the answers. Okay. Continues. All right, this one is going to be questioned about in the future. So there's my big hint on that one. People think this is nonsense, but we just got to look at the whole thing and the pieces. All right, so you have this string, it's pulling that way, and you're also pulling the block and the other block, right? So if you, just like if you had like two wagons connected together or something crazy like that, the thing is being pulled forward, this is going that way, and both of these are going along with it, all right? So with that thought, can you visualize that if you're talking about the strength the string needs to be to not break, this string has to be stronger because it is pulling A and B, but this string right here is only pulling B. So this string is experiencing more force because it has to pull A and B, but this string right here only has to pull B. I hope that makes sense in your looking and things, right? So I explained what's happening. Now's the question, right? So which of the following statements correctly describes the relationship between the accelerations of A and B, right? So if I pull this thing this way and they're all going off all together because it's all one system of things, does it make sense that A and B are going to go together, right? If I pull this and everything moves off, they're all going to go together because they're connected by string 2 right here. They're connected. So they're one system. They're going to have the same acceleration. How does the magnitude of the tension of T1 compared to T2? This tension right here has to be more than this one because this one is pulling A and B, but this one is only pulling B. So T1 is bigger than T2. That was a fast one. Zoom. 3 minutes, we can do this, all right? So this right here is our little force diagram. You have a lot of force that way and not so much force that way. And the object is only shown right here. Okay, so we don't know the motion, but we know what's happening, right? So if it was moving this way, you have a lot of friction going that way, it's gonna slow down. It's gonna accelerate that way. All right, and then it says, which of these shows a velocity? This is a velocity graph. Whenever I see a graph, I automatically think position, and at least in my thoughts. I hope you can at least have an automatic or whatever, then adjust to what's going on. This right here is a velocity graph, so it's like how fast are you going in the scenario, and it says according to what's happening, right? Yeah, okay, wait, yeah, okay. So if that right there is the bigger force, it is going to accelerate that way, which according to our XY knowledge of things is negative. It's accelerating that way, you're going to be getting slower. So it has to be a line that is coming, like there's a velocity, right? So you're going to have a lot of velocity up here and then less as you come down. So you have to be having a decrease, and then we don't have any other forces being applied onto there. So we're not having any other changes happen. So you're going to have a nice constant acceleration, which is how we always deal with things in art. We're not going to deal with jerks, which is the next thing. Acceleration, and then a change in acceleration is the jerk, but that's fancy stuff. So it's going to be B. All right, now we have a position job, position. All right, and I have my fancy little handy notes that I want to point at and, okay, yeah. Okay, wait, I drew my notes on my thing. Okay, here we go. Got my notes. It was a couple pages back. I had to go forward. Okay, so the one that's curving off up this way, right here, like this, curving off this way. If you look at your slope is getting, like at least from right here, going to have a zero slope. You're at rest for a second, and then you get faster, and that's faster forward. Like you're getting faster as you move forward, moving forward. And so getting faster. So that's not what's happening right here. So it's not this one. We are having acceleration, which means you're not staying in the same position, right? So this one is at rest. That's not it. We're not at rest. This one is constant motion moving backwards, right? So it's moving backwards because you're going to accelerate that way eventually, going something like that, which is kind of that. But this one is no acceleration. If your line doesn't change, you're not accelerating, so you're not going to accelerate. So no. Oh, clicking stuff. And then this one is the one that's left over. So dinosaur. Okay, now we got a fancy one. I got to draw a picture. It doesn't give you the picture, but you have to create one. That's why this one's got some challenge to it. I think this is like the hardest one of what we've done right here, besides that first one that had a little bit of the kinematics thrown back in there. But this one is the only forces one that's like the hardest of the day right here. So since my drawing thing is gone, yep, drawn on the board. Okay, so get rid of this. All right, so let's read it for you just in case you didn't yet. You got this box. It's being held in place against a rough, keyword rough, vertical wall, and someone's pushing on it at a 22-degree angle above the horizontal is a funny way of saying it. And the coefficient of static friction and kinetic friction are given this, and it's being held still, right? So we got to talk about our little keywords in the problem, but I'll draw my picture first, all right? So you have your vertical wall, and you have a box on it. There's your box, and you're pushing on it like so, but the angle is 22 degrees from the horizontal. So here's horizontal, and you got 22 degrees from that, which is kind of a weird way of seeing it or whatever, but we're going to end up with a triangle like so, and we're going to have to find out what is this piece and what is this piece, because we can't deal with things that aren't X and aren't Y. I don't know if Mr. Davis has told the other class that, but we can't deal with things that aren't X and aren't Y. So if they are things that aren't X and Y, like a hypotenuse right here, we have to break it up and to find out how much X it is and how much Y it is. We can deal with those pieces in our little formulas and stuff. So here comes colors. So according to my words right here, my force is 39. That's the number that's different for everybody, because my last one when I had it over here was 27, but now I got 39. So here's my number. Right there's 39. Everybody has the 22. 20. Oh no, okay. My previous one was 30, whatever, 22. Now it's 31. Changing both of my numbers around. That means you guys have different angles and different pushes, but we can handle that. So mine's 31 degrees. All right, with two pieces of the triangle, we're going to find out what's the X piece and what's the Y piece. And so I'm going to switch that to red now, and got to use your handy dandy calculator and SOHCAHTOA. So I'm just going to type in sine 31, close my parentheses, and then have 39. And sine lets you find the opposite side. So if I'm in the corner right here, the opposite's over here. Oh, I hit a button. Enter 20.1. If I go up there, change it to cosine, same thing, 33.4. And there is more happening in the picture than that, but that's just one part of it, all right? So we're pushing this thing up against the wall so that it's being held still. It wants to go down because gravity, right? Gravity's pulling down. And then we have the horizontal piece and the vertical piece of that push force. Now we're going to add in the other forces that are being applied on there. I'm going blue. Behind here. Got it. All right. Right here from the middle of the box is how we're going to draw the weight coming down this way. I'm drawing it huge so I can just get the number down here. But we don't know how much the thing weighs. That's what we're trying to find over here, the weight slash the mass, right? So mg is happening. Mass times gravity is the weight equals weight. And then there's also the wall pushing on it, which is coming out this way, which is going to be the force of the normal. And then besides that, in the little keywords of the problem right up here, it said it was a rough wall, rough. That's keywords that there is friction, even though it gives you the other stuff down here of friction. Since it said rough, rough means there's going to be friction. So if this is trying to be pulled down, friction is going to be going up against that. So friction force going up this way, the friction force, and some goodness there. So overall, we got 1, 2, 3, 4 forces, 4 happening right here. And they're in the X and the Y. So we can only deal with just the X or just the Y overall at the end. And just if you want to know a shortcut, we care about the Y in this case, which is one of the rare cases. We don't usually deal with Y, but we're going to do that. Also, since it's being held in place, you're not moving. So all of our net force is adding up to 0. That's a nice, easy, good thing for us. And so I'm just going to go ahead and write my cool equation. F net y equals 0 equals, in the y direction, you have 1, 2, 3. You have 3 forces in the y. F1 plus F2 plus F3. All right, we're going to have the weight, we're going to have the friction, and we're going to have the vertical part of the push, the vertical part of the push. So I'm going to call it the push y. So the F of the push in the y plus the force of friction plus the weight equals 0. Does that make sense? Because the weight's going down, so I'm just going to go ahead and put a little parentheses. That guy is negative down, right? So we have this part, we know from our little calculation, I already did that earlier, was my piece of the y going up. So I got 20.1. Friction, we need that cool equation. I'm going to go ahead and write the friction is fuffin, right? So the friction force equals mu Fn. That's parentheses there, right? So we're just going to take this piece and put it right there in that spot. So plus mu Fn, and then minus W equals 0. And what we're trying to find is not any of these things. Oh my gosh, what? Still not there, right? So normal force on a regular surface, which is right here, you have a regular surface right here, is equal to how hard it's being pushed into the surface, which if this is being pushed into the surface that way, right there, it's being pushed that way, this much, then that is how hard the surface is pushing back. So the normal is equal to this. So this right here is going to be this right here. Okay, all right. And then mu, they told us the static and they told us the kinetic. Static is while you're staying still. Static stay. So the static is the 0.4 mu. The coefficient of friction for static friction here in this case is 0.4. So we're going to have 0.4 times your normal, which is the x part of our push force over here. So for me, it's this. Make sure you use your number. Mine's probably different than yours, right? So 33.4. And then in regular formula, remember how weight equals mass times gravity. And so you have minus mass, and gravity in the textbook is 9.8 equals 0. I didn't put a negative right here because I have the negative right here already. We have the direction accounted for already, so don't just go adding negatives and cancel stuff out. They're not supposed to be canceled. 20.1 plus. There's our whole equation all filled out, and we want the mass, so we got to get everything all solved down for what's the mass. And it's I'll draw a little line under that to emphasize it, right? There is our final equation with everything all added in. And that's why this one's hard. This one had a lot of details in it that we haven't covered a lot. So challenge question, all of a sudden, boom, it's a box that's on the vertical wall, and we got friction you have to add in, and you have to take the angle force and break it into pieces. And if this was on a horizontal, it'd still be a little bit challenging, but this is vertical, so it switches how we normally see things. But it's not horrible if you can visualize the thing. All they did was tell you that there's a thing pushing the wall, and you're pushing it at this angle, pushing it at this angle right here. And they told you at a weird angle. They told you from the horizontal, which I always think about how it's being applied, but that's not the angle they told me, like the usual way, right? So they told us this, and you got to flip it around, find your pieces and stuff. So this one's got some nice little pieces to it. Let's find the answer, you guys. Let's do it. Okay. So maybe this one for 20.1 plus 0.4 times 33.4. Enter. And then I gotta divide 9.8 out of there. And so I got 3.4. I got pi, 3.41. But let's see. 3.42 kg. Yay! Okay. Next. We're almost done, you guys. How much time? I've been talking and talking and talking. All right, this one. Okay. Draw the free body diagram. You come in here and click on add an element. This one might be having some Flash player difficulties on some of you, but just hit refresh or allow the thing to plug into play or whatever. It'll work. I'm going to choose the force of gravity, and I'm going to scroll a little bit. I got to click right here and go like that. It's going to be, basically 270. Oh, I had it, but 270 straight down, gravity down, right? New element. We don't need gravity again, so choose the next one. Friction. Gravity wants it to go down, so friction's going to go that way. Friction, some amount. All right, and then we have the normal. Normal is going to be perpendicular to the surface. Most common error on this one is they want it to go up, which is how it is on a regular flat surface, but this time we're special. We got our thing coming off this way, and that should be good. You just have to be approximately right. You don't have to be exact on your drawings. It'll correct it for the prettiness at the end. And so I don't know if it did correct me, but I got my green. So it's down along the surface backwards and then perpendicular to the surface. All right. How would it change if it was sliding down the plane? So the first time it was being held still, so you had to draw your friction force enough to cancel out your gravitational force, but right. So the diagram is going to be the same. It's going to be the same, but the friction force is not going to be static friction anymore. Now it's going to be the kinetic because it's moving. So it's going to be the same as what we just saw. It's same as this, except instead of just being friction force, it's going to be the kinetic friction force of friction while it's moving. How would it be if it was sliding up the plane? All right, so now the friction is going to be going the other way. If it's going up, friction is going to switch directions. It's going to go the opposite way. So if I do that one, it is the friction force would be kinetic friction force, and it's going to be going the opposite direction from what it was before. Okay. 1, 2, 2 more. 1, 2, 2 more. Whoop, did I not click it? Did I not click all the pieces? I thought I did. All right, this one's another little challenge one. They have some weird wording and some little triangle stuff in here. People don't like triangles, but it's going to be all right. This is the last one, right? Oh, there's one more. Yep, okay. I have my printed backwards. So, okay. I'm going to have to draw a picture again. Now it sounds like Pandora thinks I'm not here anymore. All right, so here's our cool diagram, and they got the nice little snow thingy, and then they're pulling the like they're in Antarctica, and they're pulling the lab base station this way, and one's kind of way over here, and they probably should be closer together so the ropes don't break. This rope's going to break. That one's going to be like, what happened? All right, so here's all the little story. Mine. All right, so the weird thing about this is the horizontal cables is parallel to the line L. All right, so that's just, I don't know what's going on with these words, but I still figured out what they're talking about because I checked my answer to what they got in the thing. But you don't have to worry about it because you got me. Yay! All right, so the sum of the forces of FA and FB, right? So you have FA plus FB. They're going to be pulling it up, and FA is this much. So just weird words. Okay. FA coming off this way is, for me, was 410 newtons. All right. And then piece of this and piece of this. All right. Doesn't really look super like a triangle over here, but we do care that it's going to be a triangle. And if that angle is 50, then this angle right here is 40, or you can just say that this side over here is 50, because, you know, triangles add up to 180, you know. Okay, so we got to find out what our two pieces of this triangle are, and I'll explain that in a second. But right now we're just jumping into, there's a triangle, find the pieces. We're just going to jump into that part. On clear, sine 40, close, and 4100. This is my force. Before I had a different force also, so you have to use your force. Make sure mine is 4100. Before I had 4900. Use your number. Make sure you're not just copying me. Okay, so here's your number. Okay. So if I do my sine part, 2, 6, 3, 5, and then opposite as cosine, and 3, 1, 4, 0, 8, right? This is the one we care about at first. So if these two tractor things are pulling this thing and it's going exactly vertical, then however much horizontal this one has right here, there's some amount of x right there, and there's some amount of x right there, and those two pieces of x are equal and opposite. If it's going straight up, this horizontal, the horizontal that this tractor is applying is going to be equal opposite to the horizontal that one's applying, because if it was only this, it would go that way, and if it's only this, it would go that way. But that's not happening. It's going right there along with L. It's going that way. There's a little story. So this horizontal force going that way is going to be equal opposite to the horizontal force going that way, and we're going to use that to find what's happening with FB. So you have FB coming off this way, FB, and we know the horizontal piece of that is the same as this, 3, 1, 4, 0, 8. That's my numbers. Make sure you use your numbers. Your numbers, right? And then, so with this, and we have the angle right here is 30, which means the other angle that I care about right here is 60 degrees. And we want to know that piece right there. My board's a little bit dirty. Okay, so this is the adjacent side, so I'm using cosine. Cos 60 equals 3140.8 over h. And we want to solve for that, so you're going to divide those two things right there. And divide cos 60. 6282. 6282 newtons equals FB. That's my number. Use your number. Okay, so the whole key to doing all that right there is that the horizontal piece of A is going to be equal to the horizontal piece of B. They're equal opposite action and reaction type things. So these, according to my number that I just had, with two significant digits, is 6200 newtons over here. Yay! All right. So then now it says, what is A plus B? Since the two X pieces are going to cancel out, we only care about the Y, and I didn't find that yet in the other one. So I have the Y piece of this, and I got to find the Y piece of that. So I'm going to use the Pythagorean third this time. I'm just going to Pythag it. Okay. So squared minus 3140.8 squared, enter, second, squared, second, answer, enter. I got 5440 newtons. Alrighty, so we care about our y pieces. You got y piece B, y piece A. Take these two that are going that way, so you're going to add them. They're both going the same way. This piece plus this piece equals your total, which is what they want for the answer right there. So 5440 plus blah, 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 equals answer. So plus 2635. And so I get 810. 8100. I didn't say the other O, it's 1,000. So submit. Green. I got the green. You can get the green too. Next. Last one. Okay. So this one is a nice little challenge one also, but it's not too bad. It's not too bad, right? So system shown right here, blah blah. And so to prevent any motion is our keyword right there. If you're not going to move, it's going to stay at rest, means your net force is 0. All these forces right here added up are going to be 0. So that means that if this thing is just being held still, that right there is being pulled down, but then the friction is going to cancel it out. So overall, in our little picture right here, we care about just this guy right here, because we can zoom in on, this one has weight and the string. So this one has 2 forces on it. This one technically has 4. We have weight, normal, tension, and friction. But we do care about this one because it's what's controlling everything kind of in this scenario. If it is not moving, then it has enough friction to hold everything still, and that's what we care about in that one. So erase my stuff because I can't draw on that thing. And marker, got a marker. All right, so on A, I'm gonna draw my new picture over here. There's A, and it has a force that way of T, and it has a force this way of friction force. That's a fancy way of doing friction force. This is a fancy little F. So friction is fuffin, right? Remember that, right? So mu Fn is going to be equal to the tension, right? So that force is going to equal that one. And then the tension, if you follow it over here, is equal to the weight of that one. So tension is going to be equal to the mass of B times gravity. Mass of B times gravity, because that's what that one is, right? So, and then the normal force on this guy is on a regular flat surface, just like how we have right here, is weight is going to be equal opposite to your normal force. So our normal force right here is going to be ma, that's an A, G, right there. So I'm going to rewrite this now for what we just discovered there. So mu times ma times G equals the mass of B times G. And we got some handy dandy nice little cancellations. Gravity's on this side, gravity's on that side. Pa-chow, pa-chow. And we want to know what's the mass of A so that it will stay still. So we want to get ma by itself. Whatever. Ma equals mb over mu. And then let's see what they tell us in the story. They tell us the mass of B, and they tell us mu, solve, answer. And that's the last one. We did it! Okay, so I'm going to make another little video, kind of like this one, maybe not as long, hopefully. I don't even know how long this is. I'll find out in a minute. And it's going to be over the challenge questions. This is just the virtual day homework questions. But I told you all the answers, kind of, because you got to do your work. You do your work. You do your work. Okay, so then you'll be all right. And then I'll make a new video of the other challenge questions, but kind of like stuff like that, where you got to like do your formula stuff and the thing pushed on the wall, force stuff, and pulleys are the whoa stuff. All right, so if you've got questions, just email me. You know how to do that. You just contact me. All right. So have a good day. Hope you enjoy your awesome weekend. And then this kind of alleviates some of the thought challenge, and then you can refer back to it. And just remember, just think that I'm right, and it's all right. It's okay. Bye.